Hey everyone, welcome back. Today we're going to talk about equivalent circuits, and then we're going to derive the series and parallel rules, and then look into solving a simple series circuit, a simple parallel circuit, and a simple combination circuit. I'm going to try to go a little bit faster than last time, so the video is a little bit shorter. You can always rewind and watch it again, or pause it and look at the sheets that I have here. So I wrote everything out this time for the most part so we can see it, and I'll just kind of talk through what we have. So then we're going to start out with the idea of an equivalent circuit and what it means to be an equivalent circuit. We talked about the IV characteristic last time, and the definition for being an equivalent circuit is that the two equivalent circuits will have the same exact IV characteristic. And so right below here I have what starts out as a complex circuit. We have 3 resistors in there, and they're not all series, not all parallel. And we wanted to create the equivalent circuit for the part that is in the dashed box. And so if I cover up the source and kind of get rid of that, if I look into that circuit into this port here, these 2 terminals here define this port, I can define an I and a V. And so the IV characteristic here for this means that for every voltage that I put across these 2 terminals, I'm going to get a particular current. And so I have a set of coordinates of voltage and current points. So if I put a small voltage, we get a smaller current. If I put a larger voltage, we get a larger current. But those currents and voltages are defined according to the circuit that we have inside here. So we have a kind of a characteristic curve that goes along with this. And so anytime we use just resistors or ideal sources, all of our circuits, our IV characteristics are going to be linear. So this is called a linear circuit. And we're going to get something that looks like this. And so for whatever voltage I put on there with the source, I'm going to get a particular current back out. And the behavior is like this, going all the way down to the origin, where if you put no voltage across this, you'll get no current through that circuit. And then it increases as you increase the source voltage. The current also will increase according to this particular line. Now the goal of this is then to replace that complex circuit with a single resistor. And that resistance, then we're going to give it the label the equivalent resistance, since it's an equivalent circuit. And so this equivalent resistor, if I look at its IV characteristic, so for every voltage I put across the 2 terminals that define the port into this resistor, I'm going to get a certain current from that. And so if I make that resistance such that we get the same exact currents for the same voltages that we do in this first circuit, then we'd say that those 2 circuits are equivalent, and this equivalent resistance can then replace this whole circuit with respect to the source. And so here I've kind of shown that. Here's the IV characteristic. They're the same. So we're going to find out what that equivalent resistance is. How do we actually get that from those resistors? And that's going to be part of what we do as we move through here and look at how we solve these circuits. So it says here, if these 2 slopes are the same, then for every voltage that I put, I get the same current on both of them. So they act the same way according to any source that I put on there. And that's the idea. So from the source's point of view, the circuits are identical. They're actually not identical. They're equivalent because they don't have the exact same parts inside, but the source cannot determine the difference from that. And so we're going to use the equivalent resistance method here to simplify any of these resistor networks into an REQ. And so we'll start out by looking at how do we do that with our series rules. And so we started with Kirchhoff's laws last time, and Kirchhoff's laws help us define rules for simpler circuits, not just generic any kind of combination that we have. So we say, well, what if we only had resistors that were in series? And here we have set this up. And so I've gone ahead and drawn and labeled the nodes E0 and E1, and then all the branch voltages and currents on there here as well for R1, R2, and our source. And so if I look at the current Kirchhoff's current law, we have that the source current coming in is going to be equal to I1 going through the resistor 1, and then resistor current going into E2 is going to be equal to I2 going into resistor 2. And then we have I2 going into E0 is going to be equal to the source current going back through the source. And I've wrote out those equivalences here. So what we see is that in a series where there's only one path to go through, the nodes basically only have one exit and one entrance. And so anything that enters exits, so all these currents will be the same. And so the currents are all equal, and that is the series rule. So what about the voltage law? So the voltage law says if I start at a node and I go through all the voltage differences, the drops and rises, when I get back to that same node, I should have the same amount of energy, i.e. I should have the same voltage. There shouldn't be a change. So any change going up should be equal to all the changes coming down. And so we have here that the voltage gain from the source, Vs, is equal to voltage 1 drop and voltage 2 difference, that drop there too. So both of these drops. So Vs is equal to V1 plus V2. And so there's a relationship. And we can see if that we added more and more of these resistors in series, that we'd just be adding more terms to the right side. And so we can say that the voltage drops all add up to the original source voltage. Okay, so those are two simplifications that we can use when we're talking about writing KVL and KCL and KVL for this type of circuit. I don't have to start from scratch. I can just say, okay, all currents are equal and the voltages add up, and these are the relationships that we get. So how do I find the equivalent resistance for something that's in series here? Well, we can start this by looking at writing down our equivalent resistance. And so here is the equivalent resistance with the source, and I'm looking at this part here. I noticed that since it's only one resistor now, whatever source current comes out is the current that goes through the resistor, and the voltage that I have across these two nodes is same voltage across the nodes of the equivalent resistance. So we have IS and VS go along with that equivalent resistor. So if I wrote the equation that the equivalent resistance by Ohm's law is equal to the source voltage over the source current, and that's kind of what I want to find. So what is the source voltage and the source current? Now to get those from the series circuit, I have to go back and look at V1 and V2. And I'm going to write some element equations out here. So I have the element equation for V1 is I1 is V1 over R1. So that says that V1 is I1 R1, just algebraically. I2 is V2 over R2, so V2 is I2 R2. And so setting those up for V1 and V2. I'm also going to expand this equivalent resistance here. So what is the equivalent resistance when I look at the source voltage? So we have the source voltage here using the KVL. I can plug in that the source voltage is V1 plus V2. So I can plug that in right there. And so that's over the source current. And then I can use the element equations to substitute in for V1 and V2, and that becomes I1R2 plus I2R2 over IS. And then I use the KCL idea that the currents are equal to substitute in for I1 and I2 is just IS, and then I can distribute that out, and we notice then the IS's cancel out, and so we get that it's R1 plus R2. So the equivalent resistance when I look at the series combination is just going to be the sum of those two resistors. So Req is R1 plus R2 plus all the way down to however many that I have. And there is the kind of result there. The equivalent resistance is the sum of the individual resistors. So those are our rules. So KVL and KCL are reduced to the currents are equal, the voltages add, and to solve for equivalent resistance in this particular situation, we just add those resistances up. And now I want to look at the parallel rules derivation. So again, here I have a parallel circuit. I've defined my branch currents and voltages and the two nodes E0 and E1. So KCL in this case says that, hey, the source current is entering node 1, and then we have two exits, and that's I1 and I2 that go through these two element resistors. And so if I wrote the KCL, the source current entering that node is equal to I1 plus I2. And if I were to add more, we can see we'd add more pass down here. So the currents add. So that's the parallel rules. KCL simplifies to the currents add together. The voltage, so if I look at the loops we have here, so I have V source voltage for the source, we rise. And then if I go around this loop here, we're going to drop through V1. So those must be the same. So Vs equals V1. If I go through the source and go through V2, so Vs and V2 must be the same. And then V1 and V2, if I go around that loop, we see there's only one rise and one drop. So those have the same value. And you can see that across each of these, we've established the node voltage. This whole top node is E1 and this bottom node is E0. And so the difference between the two nodes, the terminals on each of these elements is just the difference between these two nodes, and they're all equal. So the voltages are all equal. So we can simplify KVL for parallel circuits that the voltages are all the same, which is kind of cool. So element equations here, I wrote the element equations in the conductance form because in deriving the equivalent resistance, it's actually a little easier to go through the conductance method first. So the current here, according to Ohm's law, is the conductance times the voltage for element 1, and the same for element 2. And so here's the equivalent circuit. We want to find the equivalent resistance and the equivalent conductance, and I've labeled everything again in this circuit. So just like we did in the last one, we're going to start out by writing the equivalent conductance. So the equivalent conductance is not V over I, it's I over V. So I can see it's the source current divided by the source resistance, because these are shared between these two elements, since it's just the very simple circuit that we derived earlier. And so now I can start to use my KCL and KVL to plug in here. So the source current, we said, was the sum of I1 and I2, so I plug that in, and then we leave the source voltage alone. Then I can use my element equations, and so the element equations here, I1 is G1V1, so I can plug that in, and G2V2 for I2, and then I can go ahead and distribute out, first then I replace the V's here, since KVL says the V's are all the same. So V1 and V2 are actually equal to V source in our circuit, and I can distribute out the V source, and that's also on the bottom, and we can see that those will cancel out and we get G1 plus G2. So the idea in a parallel circuit is that every time I add a path, it makes it easier and easier for the current to flow through the source, because there are more paths to flow through, and so the conductance grows, and so we say the conductance is add every time that I add another path here. And so here is a general equation for conductance is adding. So GEQ is G1 plus G2 all the way through however many elements I have in parallel and strictly parallel. So in parallel circuits, the conductance add, and that's equal to the equivalent conductance. Now, conductances aren't something that I usually want to end up with, since we're given R values, not G values. And so is there an easier way to look at this when I solve for like an equivalent resistance, if I wanted to find the equivalent resistance? Well, remember that conductance is just the inverse of the resistance, so I can substitute 1 over R for each of these terms, and I get the equation 1 over R EQ is equal to 1 over R1 plus 1 over R2 plus all the way to 1 over Rn. And this is what you've learned it as before, but you probably didn't know where it comes from. And so there's where it comes from, is that the conductances add in parallel. And so this is often helpful to use the resistance equation so I can directly plug in to the ones that I want. So a quick summary of what we just looked at then is, we're connecting a source that has its IV characteristic and to different complex networks. So here's a complex series network, and we want to find an equivalent IV characteristic that belongs to just one resistor. And to do that, that resistance has to be the sum if it's in series. We also said for KVL and KCL that the voltages add and the currents are equal from the Kirchhoff's laws. And so just to kind of look at this in terms of IV characteristic graphs, I'm going to attach this source to one of these resistor characteristics. And so this is the same for this complex circuit. It's the same it is for the simple circuit. So I could use either one with the source and it'd have the same outcome. And so we're going to do it with the simple one because that's easier to analyze. And so when I do that, they have an intersection point that decides, determines the operating point. And so that would determine, for this case, since it's a voltage source, what corresponding current source current we would get for that circuit. So that's our goal. In a parallel sense, same thing, complex turns into a simple one, different way of finding the equivalent resistance, but the application here is nearly identical for the going the current direction, except that we would know, we're using a source voltage for this one too, so you would know that voltage and that IV characteristic when we find the source current. So parallel, voltages are always equal and currents add, and that is again from KVL and KCL. I want to show you one quick shortcut that we can use when you're doing parallel equivalent resistance calculations. So if you limit yourself to 2 resistors, we can do some algebra here to make kind of a what's called a notebook equation, and so that will work only for this situation specifically, but we can look for these, and they're often there in simple circuits, so we can make life a little bit easier. So instead of like taking the whole 1 over R1 plus 1 over R2 and so on and so forth, if I just look at this and kind of start to rearrange, if I only have 2 resistors, I can easily find a common denominator here is R1 times R2. So I multiply this side by R2 over R2, I multiply this term by R1 over R1, and I end up with 1 over REQ is R2 over R1 R2 plus R1 over R1 R2. And then I can combine those underneath over one denominator. So that's R1 plus R2 over that product term R1 R2. We're looking for REQ though, not 1 over REQ, so I have to invert it. And when I invert it, then I invert the other side. And so I get the product R1, R2 over the sum R1 plus R2. So this is a really quick one, a nice one to have in your back pocket. If you just, not too hard to remember, it's just the product over the sum. And then you can quickly simplify 2-element parallel resistor networks in that fashion. So I do want to do an example, and so in this case I will actually write this one out. And so here is our example of a series circuit, and we have our source voltage is 20 volts, and we have an 8 ohm resistor 1 and a 2 ohm resistor 2. And this is generally how we receive our circuits, because we buy resistors by their values, and so you're going to most likely know when you're designing what values you're going to be able to get. And when we attach batteries or sources, we often know the voltage. And so voltage and resistances is a common starting point for analyzing circuits. And I want to put in all my corresponding branch voltages and currents. So I'm going to go ahead and write my IS right here. And so what is my IS going to be? And then I want my I1. And I also want my V1 and what that value is going to be. And then I have my I2 and I want my V2. And so we'll have values for these as we solve the circuit. So what is the process that we'll use to solve this? So the first step is generally to find the equivalent resistance. Since this is parallel, this is pretty easy. REQ is just going to be R1 plus R2. And so adding those together, we get 8 plus 2 is equal to 10 ohms. So great, we have our equivalent resistance based on the series equivalent resistance formula. And so now this turns this circuit into something that looks like this with just one REQ. And we know that this value here is 10 ohms. And so since these now will share the same voltage and the same current, and I already know that the voltage here is 20 volts, I can use this to find my operating point. And we're gonna do this we can do this using like our element equation or looking at the graph for the IV characteristic. And so to find our operating point, and when I say operating point, I mean what is the source current and voltage on our IV characteristic. And so here it is. We have our IV. So I just determined that the equivalent resistance is 10 ohms, and so if I draw the line for the IV characteristic for a resistor, it's Ohm's law. I is equal to V over R. And so this is I is equal to V over 10 because we have an equivalent resistance of 10 ohms. So that's what this is showing right here. I is equal to V over 10. And now I don't know what I is because I don't know what V is. So if I know either I or V, I can figure out what the other point is here. And that's what where the source comes in. So I have a 20 volt source. So I also going to have 20 volts here. And that's the source characteristic, IV characteristic. And so then we have an intersection point. And so if I plug in 20 volts over 10 ohms, this turns out to be 2 amps. And that's my source current. And so there you can see it operating on the IV characteristic graph. And so that 2 amps can go directly back into my circuit, and I know that's 2 amps. Then the next thing that I'm going to do is I have my equivalent circuit, and I need to expand that back out. So for my third part is expand. And in this case, I'm going to use the series rules. And so we're going to look at, I'm just going to break off the resistive or load portion of the circuit. So this is REQ. We know this is 10 ohms. And we have a voltage and a current coming in. And I already know what those are as well. The current coming in here is 2 amps. and the voltage across here is 20 volts. And that I got from the equivalent circuit right here, 20 volts, and this is 2 amps coming in. And so I want to turn this back into our original circuit, and our original circuit had 2 resistors, like this. And so this is going to be our 1, and this was 8 ohms, and then R2 is 2 ohms, and we want to know everything about this. So I want this voltage, and I want the current coming in here, and the current coming into this one here. So we're trying to find these branch values now as we expand back out. So to do that, we have our element equations, and that we get from our expanded circuit there. We have I1 is V1 over R1, and we have I2 is V2 over R2, and we have our circuit equations. Now when I say the circuit equations, those are KVL and KCL, but in this case we're using series rules, so those become a little bit easier, and I know that the currents are all the same, so I know that I source here is equal to I1 is equal to I2, and that's 2 amps. So all of them have 2 amps as their current, 2 amps, 2 amps. And then I know that V source is going to add up to V1 and V2. I don't have that solution yet. So what I can do now, since I know that these are all 2 amps, I can plug that back into my element equations, and then rearranging these to find, or I guess I don't have to, I can just plug them in. 2 amps is V over R1, which is 8 ohms, and 2 amps is V over R2, V2 over R2, which is 2 ohms, and then multiplying these, I can find V1 is 16 volts, and then V2 is 4 volts, multiplying those across. And so I can now plug these back into my original circuit. We said this was 2 amps, this was 2 amps, that's 16 volts, and that's 4 volts, and I found everything else about my circuit. I've used this equation, I've used this equation, I've used this equation. The only one that I haven't yet used is this. Vs is V1 plus V2. So I can actually use this to check. And so I'm going to use this to check that my answer was right. So Vs was 20 volts. V1 here we just found is 16 volts plus V2, which is 4 volts, and indeed they add up to 20 volts, so we can say that that has been checked. So there it is. So for any source that I connected to this circuit, it had the same voltage and current coordinates that I would see for any source that I connected to this circuit. So these two are then equivalent, and I use that to find all the values of my circuit. Parallel example. So similar here in our parallel example, I want to break this or convert first into finding my equivalent resistance. And so I'm gonna use the shortcut here. So we said there's 2 equivalent resistors, so we can find that equivalent resistance as the product over the sum. So this is R1 times R2 over R1 plus R2. And if I do that, oops, excuse me. And if I do that, I get 4 times 7 over 4 plus 7, which is equal to 28 over 11, and that's 2.55 ohms. One thing you notice here that in parallel, since it becomes easier for the current to flow, we expect the overall or equivalent resistance to be lower than either of these here. So 4, 7, 2.55 is less. Opposite for series, it always got bigger because we added those up. All right, so the equivalent circuit here then looks like this. Let's go ahead and attach our currents and voltage labels here. There we go. And we have the equivalent resistance now. This is 2.55 ohms. And then I also am going to look for the voltage and the current here. Well, I already know the current because this source has a 3 amp current associated with it. But what about the voltage? So to find that voltage here, we're in essence going to be finding the operating point. And so just like we did before, I have my IV characteristic. There is the equivalent resistance. So this I is going to be V over my equivalent resistance, which is now 2.55 ohms. And in this time, we have a source that's a current source. And so I know the I value, so coming around this way here, this I is going to be 3 amps. Again, this is current and voltage here. So I found my operating point by finding the intersection there. And so I know I, and I'm solving for V here, so V is 2.55 times 3, giving me a 7.64 volt source voltage. So this is 7.64 volts. So I've found the source voltage here, and that would also be the voltage across my equivalent circuit. So the next thing I'm going to do, so that was part 2, is to find the operating point. So the third thing we're going to do now is expand. We want to find all the branch quantities, and we're going to expand using parallel rules. And so this guy here is going to be expanded out to the original, right? To find those values inside there. So I'm going to write out the element equations. And I'm going to write out the circuit equations and use those to help us solve this. The circuit equations are just KVL. So since this is a parallel circuit, I know that the voltages are the same. So I'm going to start there. So the voltage of the source is V1 is equal to V2. And we have that voltage at 7.64 volts. So I can just write that in right here, 7.64, 7.64. And 7.64 volts. So we know the voltage across all those paths. Now I'm left to find I1 and I2. The other equation I have is that the source current splits, and so this is 2 parallel paths, so the current is going to split down those 2 paths. But I don't know that complete answer yet. I'm going to use the element equations to help me out. So I1 is V1 over R1, I2 is V2 over R2. These are the element equations, the characteristic equations for those 2 resistors. And we already know V1 and V2 here, and we know R1 and R2 from the original diagram, so I can find these as I1 is equal to 7.64 over 4 ohms, and that gives me 1.91 amps. And then this is 7.64 over 7 ohms, and that gets me 1.09 amps. And then I can do a check here. 1.91 plus 1.09 is indeed equal to our 3 amps. And so it all checks out. Great, so I can add these in. So this is 1.91 amps, and this one is 1.09 amps, and I'm done. One more thing that we haven't talked about is power. And so I'm gonna just go ahead and do power. We have power delivered by the source and power received by the loads or the resistors. And remember, our power equation is P is V times I. And then so for the source, this is V source times I source, which is 7.64 multiplied by 3, and that gives me 22.9 watts. And then for R1, it's V1 times I1, and so that's 7.64 times 1.91, and that gives me 14.6 watts. And then for R2, I have V2 times I2, 7.64 times 1.09, and that gives me 8.33 watts. And so in a circuit, we're taking energy from the source, and the source is adding energy to the charges as they move around and delivering them to the resistors. So the amount of energy that I add is going to be equal to the amount of energy that I deliver. And so we can see that if I take 22.9, that's equal to 14.6 plus 8.3, 3 watts. So again, we show that that is correct. This is conservation of energy. All right, great. So there's our parallel example. And the last one, we'll do a combination example. Make sure you guys can see everything here. Oops, looks like I've changed a little bit of my focus. Hopefully don't have to do this whole thing again. Okay, great. So, combination example here. So again, I want to find everything about this. So there's my source current, and I'm going to have my current into R1, plus and minus there for the voltage, plus and minus for the voltage here, the current into R2, the current into R3, and plus or minus for the voltage. All right, so so we have a not strict series and a not strict parallel situation here, and I want to figure out everything about everything in this whole picture. Okay, so we can't do it in the equivalent resistance in one shot, so we're actually going to work from the further side back towards the source. So we're going to work towards that source as we find equivalents. So let's find the first one. So the first thing I'm going to do if I work from the right side is I'm going to have to take care of these two resistors. And these two resistors, as we can see, are in parallel. So we're going to combine those in parallel. So I'm going to take this and turn it into an equivalent resistance for these two guys here. So this is going to turn into a picture that looks like this. And again, I'm going to take out the source. And we're going to still have R1 here, but instead of this parallel combination, we're going to have an intermediate equivalent here. So I'm going to call this REQ1. And so we're trying to find out what REQ1 is. And so how did I get REQ1? Well, this is a parallel combination of R2 and R3. And so I can use this. I'm going to use the old kind of method here of doing that. And so I can say 1 over REQ1 is equal to 1 over 20 plus 1 over 80. And if I then evaluate 1 over 20 and 1 over 80, we get 0.05 plus 0.0125. Okay, what you might realize here is that this is 1 over a resistance, so that's a conductance. So what you found here is the conductance 1 and the conductance for 2. Okay, and so then if I evaluate that, I get 1 over REQ is equal to 0.0625, and this is the equivalent conductance. And so the equivalent conductance is 1 over the resistance. So if I want the resistance, REQ, I have to take 1 over that, 1 over 0.0625, and then we get a value here of 16 ohms. So the equivalent resistance is 16 ohms for just that parallel combination. And so that's our first step of finding the equivalence. The next step is we're going to turn this into simply one resistor. I'm going to call that REQ2. And so how do I do this? So these two are in series. So this one was parallel. These two are in series, so I have to combine these in a series fashion. And so the series REQ2 is going to be R1 plus REQ1. and so we have a value for that. REQ1 is 16, R1 is 10. So we have 10 plus 16, and that gives us 26 ohms. So in that fashion, we found the equivalent resistance to be 26 ohms. So the next part, so that was part 1, and so I'll just kind of write that right here, is finding REQ. Part 2, finding our operating point. So just like we did before, we're looking at this IV characteristic now that has the relationship I is V over 26 ohms, because that was our equivalent resistance. Once we found that, that's what it should look like. And in this case, we're giving a source voltage that's 40 volts. And so the intersection here with 40 volts and this will give us our source current. And that'll be our operating point, 40 volts and whatever that current is. So I just plug in, so I is 40 volts over 26 ohms, and that gives me a current of 1.54 amps. And so this is 1.54 amps. And so I've determined my current through the source. All right, so to continue, the next thing we have to do is expand back out. And so we're gonna expand first REQ2. So we're gonna take this and turn it back into this. All right, and so to do that, I'm going to use my my branch. I'm going to use my circuit equations and my element equations here to do that. So my element equations, now I'm looking at expanding out here, so I'm going to use these ones. So I1 is V1 over R1. And then I have one for our EQ1 too. So IEQ1 is equal to VEQ1 over REQ1. So those are two element equations for those. And then I have my circuit equations. And this is a series. So I took this and expanded it out into a series. So this is going to be series rules. And so in series, the currents are all the same. And so I'm looking at the current through REQ, so that's IEQ2, so I can call that IEQ2 when I do this. It turns out that IEQ2 is also, our source current, so these are the same. So if you wanted to write IEQ2 or I source here, I think that doesn't matter too much. That's going to be equal to I1 and IEQ1, and we do have a value for that. That's 1.54 amps, so we already know that. So I'm going to take that and use it in my element equations in a minute, but first let's write the voltage rule here. So voltage source here is going to be V1 plus V EQ1. So the voltage drop across that and that are going to be equal to each other. So now let's plug in here to find to find V1. So I have I1 is 1.54 amps, and that's equal to V1 over R1, and R1 we know is 10 ohms up here. So 10 times 1.54 gives me a voltage of 15.4 volts. So across R1 is 15.4 volts. And I can actually add that right back into the complete circuit here. And so I1 also that I know as being 1.54 amps, I can put that here. And you can see that makes sense because it's in series with the source, so they should both get 1.54 amps. And there we have it. So I could solve for this now to find the current and the voltage drop across our REQ1, but I'm actually going to use this equation because it's going to be a little bit easier for me to do. And so we're going to ignore this because we do have a redundancy here. So the source voltage we said was 40 volts, And now I just found the drop across R1 is 15.4 amps. And so how much more do I need to drop across that? So 40 minus 15.4 gives me an equivalent voltage here of 24.6 volts. And so this is going to have a voltage drop across it of 24.6 volts. Now that's neither these right now, we don't know that, so it's just for our equivalent resistor. We still have to expand that out. So what I want is the current here is 1.54 amps through the equivalent resistance, and the voltage across it is 24.6. And then we're gonna expand that one out next. So the next step is to expand REQ1. And so we're taking REQ1 and then turning it into what it came from, and that's a parallel combination of resistors. And this is R2 and R3. Oops. This has a value of 80 ohms, and this has a value of 20 ohms. And then we're going to find the voltage drops across them and the currents into them. Okay, same method that we're going to use here. So I'm going to take my element equations for these two. So I2 equals V2 over R2. I3 is V3 over R3. I'm going to take my circuit equations, and in this case they're parallel. And so in parallel, the voltages are the same. So we have the voltage now we're looking at is the voltage across what we're expanding from. So this is not the source voltage. So this is the voltage for EQ1. And so I know that from the last example that we had 24.6 volts, and the current here was 1.54 amps. So these are the quantities that we have to use when we're expanding here. So this is VEQ1 is equal to V2 is equal to V3, and that has a value of 24.6 volts. So great, I already have these values, 24.6 volts. And in parallel, the voltages are the same, so that's what we took over and showed that. And so how do I get the currents? So this time I have the currents directly here in the element equations. All I needed was this voltage, so we don't even need to use that IEQ1 is equal to I2 plus I3. It's going to be redundant. I can use it as a check. So I'm just going to plug in here. So I2 is V2, which is 24.6 volts, over my resistance, which is 20 ohms, and that gives me a value of 1.23 amps. I3 is V3, which is 24.6 volts, over R3, which is 80 ohms, and that gives me a value of 0.31 amps. This is I2. And if I wanted to do the check, remember that our current through the equivalent resistance REQ1 is 1.54, and so 1.54, 1.23 plus 0.31, and indeed that does check out. Okay, thanks for watching. Hopefully that was helpful for you to figure out how to solve these circuits. I did a lot of work here. You don't have to show as much work as I did when you're doing this, as long as you can kind of take it back and fill out all of the values in the original circuit. So let me just actually do that before I sign off. So the goal was to kind of put all of the values into the original circuit here, and so this one's nicely labeled so I can finish this up to do that. So we already have 1.54 amps and 15.4 volts here, and we said the current in this path is 1.23 amps, and the current in this path is 0.31 amps. And this had a voltage of 24.6 volts and 24.6 volts on both of these. And so we can do a quick check with Kirchhoff's if you wanted to. So flow in is 1.54, flow out 1.23 plus 0.31, that is 1.54. And any loop, 40 volts, 15.4 drop, another 24.6, 15.4, another 24.6, both add up to 40, 24.6 and 24.6, they're the same. So that looks like a good solution. All right, thanks a lot.